Okay, let's proceed with the tutorial. So what is the definition of the capacitor with two electrodes? So the definition of the capacitance, you remember? So that would be the capacitance is given by C, and the value is, not the value, but the definition is capacitance is charge over voltage. So how do you assess the charge on the capacitor? So first of all, it is important to remember that C, don't mix up the letter C for the capacitance with the unit that we also have, which stands for Coulomb, which is ampere times second. So the capacitor is a function of material parameters and geometry. So epsilon is basically the material, it includes the material properties, and then you have the geometrical properties. And if you look at the parallel plate capacitor, then you have an electrode 1, and you have an electrode 2. This is your electrode 2. And in between, you have some material, possibly. It can be also vacuum. It doesn't have to be material, but you can have it filled with some dielectric material, so it should not be conducting. And this is given, this has some epsilon given. And then these plates have a separation. This is a specific example for a parallel plate capacitor, but the formula that I've given here above, the C is Q over V, that holds for any arbitrary capacitor geometry. And what is also important in that context, what is the charge on that capacitor? Well, the charge you can obtain by applying Gauss's law, by doing a closed surface integral over one of these electrodes, over the electric flux density. And again, D is standing for the D field. It is the electric displacement field. You can just as well call it the electric flux density. That is all the same. And the D field is related to the electric field via the permittivity. You have usually a permittivity epsilon naught, which is the one of vacuum. That's a dielectric constant. Epsilon naught is roughly 8.54 times 10 to the minus 12 farad per meter. Or that means this is also ampere second per voltmeter. You see, the unit of the capacitor is also farad. Capacitor unit of C, that is farad, like in honor of Michael Faraday. So that would be, as you see, it is charge over voltage. So it is ampere second per volt, the unit. Also, what you need for the determining the capacitance, so we say it is the ratio of charge over voltage. You need the charge that you obtain from applying the Gauss's law. You're taking here, for example, make your control volume like this here. Then you apply here Gauss's law. The second thing is what you need is a voltage. And there you take the voltage by integrating from the electrode 1 to electrode 2 over the electric field. That will give you your voltage. So this here is general, right? This is now, when I say that it's depending on geometry, then that means you see that already here in this example with the parallel plate capacitor, the size, the surface, or the area of these electrodes is mattering. So they are part of the geometry. Also, their separation of these two electrodes. It's also part of separation. So this is a specific example of the parallel plate capacitor that we have here. And there we had found in the lecture that the capacitance is given by the permittivity times the area divided by the separation, the plate separation. And now actually I wanted to also say that this here, this epsilon 0, epsilon naught, this is our dielectric constant. This is basically for vacuum. But as we have seen also, it is pretty close also the one for air, because when we have any arbitrary material, then we say usually that our material E1 is given as a product of this E0 and a relative permittivity of that particular medium. So while this E0 is this 8.54 times 10 to the minus 12, the relative will be something which is a bit more than 1, or it could be 3, 4, factor 5, something like that. So this relative permittivity is in the range, or we had it for water actually. We had said pure water has a relative permittivity of 80, but so even though they look so similar, this E naught is this 8.54 10 to the minus 12 farad per meter. And the E relative is something that ranges, it is larger than 1, and it can be something between 1 and I don't know how much, but usually it is just a rather small number like 4, 5, 6, or for water it could be 80, and it's unitless. This is a relative permittivity, no unit. Now let's look at the example of the spherical capacitor here. We have here the picture of two concentric, perfectly conducting hollow spheres, and they have a radius R1, the first one, that is shown here. This is basically the capital one then here. Or let's make it the other way around. This is basically our R1 and this is our R2. And then you have a charge that is on these spheres, and the spheres carry opposite charges Q. So meaning the one here carries a charge, for example, plus Q, and the outer sphere carries the charge minus Q. So now we also have a dielectric material inside the sphere, and that let's denote as E. This is epsilon, that shall be our epsilon naught times epsilon relative. And we want to calculate the voltage between the spheres and the capacitance. So we want to get to C is equal, this is a definition of the capacitance, how much charge per voltage is this capacitor holding. That means as you increase the voltage, that holds more charge, but this ratio, that is a function of the geometry and of the material parameters. And we want to calculate first the voltage that we do by integrating the E field from R1 to R2. So first step, we need Gauss's law that tells us that the charge enclosed is the whatever is in this control volume. This is a virtual volume. And we obtain whatever charge is in this virtual control volume by integrating over the closed surface area of that control volume over the electric flux density, over the electric displacement field. So, okay, just what would happen if you were integrating here over this volume? Well, I'll remove that again because this is not what we're interested. But here you see in this volume, there we have included a charge Q plus on the inner sphere and a charge Q minus. So the net charge is just canceling out, right? So this would not give us any total charge value if we evaluate here if you apply here Gauss's law to this control volume. What we are picking as a control volume rather is a sphere inside here. And now we are in the comfortable situation again that because of symmetry, we only have a electric flux density in radial direction. Because of symmetry, we have a D field which only has a component in the ER direction. And we know that the electric field is obtained by taking the D field and dividing it through the permittivity of the material. So we also know, because that is given as a problem statement, that the charge on the inner sphere is given as Q. So we know that Q over the control volume accumulated is the charge plus Q. And now we insert that on either side. So we have the evaluation of our flux integral. Flux quantity is dr times er. And the surface, the differential surface element, for that you have to consult the mathematical formula sheet, but we are in the spherical coordinate system. You know that this is given again by this r square sine theta d theta d phi. And we have looked at that closely in the previous problems also, where we have already done that for a spherical setup. We know that this is 1 here. This is an inner product of two identical unit vectors. So we know that the surface integral, if we integrate over the theta and phi component, that gives us 4 pi. And then we are remaining here with r square and the dr. So the dr here, this r is an index here, right? So you know that you have here 4 pi r square dr is plus q, and then therefore your dr is just q over 4 pi epsilon r squared. And now we're just one step away from getting the electric field that is also aligned with the displacement field, and that is q times 4 pi, and sorry, I have been a bit too fast here. The previous one was, of course, r square, and now we have the epsilon here. So this is our electric field. Now we set the voltage to compute between these two spheres is obtained by integrating from the radius r1 to r2 the electric field, and it has only this r component, and we are only also integrating along r. So again, this here, this dr is basically, you can write that again as er times dr, and then this and this will be 1. So you get integration from r1 to r2 over the er, which is now here all completely free of vectorial elements. And then you have integration from r1 to r2. We insert this q 4 pi epsilon r square dr. And this, then you integrate this, then you get here 1 over r squared gives you 1 over r here, and here 4 pi epsilon. integration borders are R1 and R2. Insert these borders, you get this Q 4 pi epsilon. Okay, I pulled out the minus now. And that's why I interchanged here this order also. So this is Q over 4 pi epsilon R. Let's bring that all onto one line here. Then that would be R2 minus R1, and here R2 times R1. So that is your voltage. And now we can right away tell what the capacitance of this spherical capacitor is. It is Q divided over voltage, and that is this plus Q divided by this voltage 1, 2 that we here computed, and that is Q over Q 4 pi epsilon R2 minus R1, R2 times R1. And that is then the Q cancels out, the 4 pi epsilon we put on top, and there's R2 times R1, and this is divided by R2 minus R1. This is a nice thing to appreciate, is that now you have the capacitance and you can apply an arbitrary voltage and you know what charge it is. This is now quite a universal formula to use. If you have, or the other way around, you put a charge, you know what voltage you will have. So this is quite useful. And this is purely a function of the geometry. And you can even now vary the radii of the two spheres, and you can get it with different geometrical properties. Let's do another capacitor problem. That would be the problem 13. And you see, this is again some plate capacitor, but however, it is not parallel plate anymore. So we have a plate capacitor that has the shape of a cylindrical segment with the angle phi 0. So you see, you have one plate here. There's your coordinate system. This is your origin, and this is your r direction. And the one plate here, it starts at the radius r, and it extends to 3r, but it has two regions. Region 1 is extending from r to 2r, and the region 2 is extending from 2r to 3r. And then you have the second plate that is up there, and that is, as you see, at an angle, and the angle is given as phi 0. And with respect to z direction, so this whole thing here is a cylindrical problem, because this is in the z direction, which you have here. There it is uniform, and it extends with a length L. And this length L in z direction, that how far the plates are extending, is very large compared to R. Why is this important? Because if this plate is large, we can assume that we can neglect here the stray fields. And also, in the end, we can neglect the stray fields, and we can basically reduce this whole problem to a two-dimensional problem in cylindrical coordinates. So we have these two dielectrics placed between the electrodes. The first one in the region 1, which I just mentioned, and the other in the other one. And the first has epsilon 1, and the other one has epsilon 2 as a permittivity. Now, it gives us the electric potential phi of phi. And so this is a capital phi, and this is a small phi. The capital phi is the potential, the small phi is the angle in the interior of the capacitor. And this is the value for the potential. Now, first task is sketch the equipotential lines and the electric field lines between the two electrodes. Draw two separate plots. Okay, let's do that. We have A, this is R, two plots. So this is phi, Here's phi. And what are the equipotential lines? So you see the potential is given here, and it has only a dependence on phi. That means if you have a constant phi, you're running on an equipotential line that you see immediately. So that means we have here our lines. So the phi is minus k times a small phi. And we have at the complete angle between the two plates, that would be phi 0. And here at the bottom, we have phi equal to 0. And up there, we also, of course, have a potential down here and here. And up there on the top electrode, there will be phi is minus k phi naught. And as for the charges, we have positive charges here and negative charges here. What about the field lines that we also should plot? Well, we know that the field lines are perpendicular to the equipotential lines, and for that reason they have this radial character. And these electric field lines we obtain by taking here the negative gradient of the potential function. Also here, of course, the electrode, it starts here, ends here. It doesn't, that's where our electrodes are. This is our electrode. We also can name it A, and our electrode B. So here we have the equipotential lines on the left-hand side, and we have here the electric field lines. Problem B is now calculate the electric field in the capacitor. Well, the electric field is given by the negative gradient of the potential function. And what is the potential function? It is k minus k times phi. So what is the gradient of phi? For that, you have to look in your mathematical formula, and you'll find that this is partial derivative of phi with respect to r, that is the r component, then 1 over r d phi that you find in your math formula sheet. But be careful, there in this math formula sheet where you find the gradient, the r is denoted with a rho, which looks very close to the phi. So you have to be careful. If you go in your math sheet, you will have there a phi and you will have a rho. And don't mix them up. The rho is your r. So the second component is a set, the phi, and the third one in the coordinate system is a set. And now you do that, you take the derivative. There's no r component in the potential, so the derivative with respect to r is 0 then. There's a phi component that will give you minus k, but be careful because we are in cylindrical coordinate system, you have to put the 1 over r in here too. And for set, there's also no set dependence. So, yeah, mind, this is minus k phi, that's the potential. So the electric field is now 0, k over r, 0. And that means it only has a E phi component. It is k r times E phi. And that is basically minus the gradient of phi. Okay, now we have the electric field. Now we can calculate the voltage between the two electrodes. And the voltage between A and B, so the one electrode is named A and the other one is B. Voltage is obtained by integrating the electric field over the path. And that electric field we said is K over R times E phi. And the line element, and there you have to again consult your math formula sheet. The line element here is dr, r d phi, and dz. And if you think of depicting that here, you have these two plates tilted here, and you want to know what is the voltage, to measure the voltage here, then you have to integrate somewhere around this path, which is basically aligned with the phi direction. That turns to be out to be advantageous if we do that, because our E field lines are like this. This is our E field. You see the E field has a phi component, so let's choose also the integration path along that. There are no, so we're integrating from 0 to phi naught k over r times r v phi, and that would be k times phi naught. So this is our voltage. Now the next problem is decalculate, for that use Gauss's law, the charge on the lower electrode, that means at the angle phi is equal to 0, and for this purpose determine the electric displacement field in the interior of the capacitor. Differentiate the regions of different permittivity. So let's use Gauss's law. This is radial direction. Back into the plane here is z direction. Here up there we have phi. And so we have here a second plate and here the first plate. And we want to, there's our plus charge, there's our minus charge. There are our electric fields on the field, the electric field. And now we want to do a surface integral here. Well, actually, it is a closed surface integral. And this has here some normal element here. And if you look at it a bit closer, we also want to make a distinction between the two regions where we have the two different material properties. So we have here R, 2R, and 3R. And we have here an epsilon 1 and epsilon 2. And let's integrate over this volume here. So our differential surface element. So then you have to consult again the math sheet. What is a differential area element? Because we are in cylindrical coordinates. So that is actually quite good. It is dr times dz, and the normal vector is E phi. Our D field is permittivity times electric field, and the electric field is k over r, and it is oriented in phi direction. So we have to make a two-step integration, one for the volume that extends from R to 2R, and then one for the volume that extends from 2R to 3R. So we apply Gauss's law. The charge is obtained by taking the volume integration. In terms of z direction, it expands from 0 to the length L. That would be for z. And in terms of R, we go from R to 2R. And in our first section, we have for the D field, we have the permittivity 1. The E field is determined to be this, k over r, E phi. And this is our differential line element. This is also in phi direction, the normal vector, dr times dz. And the second contribution that runs then from 0 to L in z direction, and it runs from 2r to 3r in radial direction. So this is a material epsilon 2. We have here k over r again, E phi times E phi dr dz. Well, then as for the integration in z direction, because it's uniform in Z direction, that will just give us a factor L. The K is also not affected here, that we also can pull out. So we have here an integration over 1 over r. And if we integrate that, so for the first medium, of course, we have a e epsilon 1, and we integrate 1 over r, which is a logarithm of r, from r to 2r. And in the second area, we have pulled out the L and the K, and then this gives us epsilon 2, and we integrate over for 1 over r, so that gives us a logarithm of r running from 2r to 3r. Mind, the logarithm of 2r minus logarithm, natural logarithm, is actually 2r over r, right? So if you make use of that, then this here will become L times K times epsilon 1 ln of 2 plus epsilon 2 logarithm ln 3 over 3 half. So you have the charge. Nice. Now you just need to, in order to get the capacitance, we have computed the voltage, we have computed the charge. Very easy at that point. We just have to take the ratio charge over voltage. That would be L times K times epsilon 1 ln 2 plus epsilon 2 ln 3 half. The whole thing here divided by the voltage, which is just K times phi naught. You see here, you can cancel out that K. And this here is L over phi 0 epsilon 1 ln 2 plus epsilon 2 ln 3 half. And finally, we want to calculate the energy which is stored on the capacitor. And the energy we have seen in the lecture is given as, for the capacitor, is 1/2 C times voltage squared. That is 1/2 L over phi. It's the capacitance. E1 ln 2 plus epsilon 2 ln of 3 half, and the whole thing multiplied by the voltage squared, which is K times phi 0. Or alternatively, we can also give the electric energy as 1/2 electric field times the flux density. And for that purpose, then we would have to integrate the electric field over the volume. Sorry, that is a this is a density. Quick here. This is a small. This is the energy density. This is a small. And the large one, the complete energy is basically integrating the energy density over the volume. So here, this is something where you have joule per cubic meter as a unit. This is the energy density here. And this here is the energy that you obtain by integrating, taking the volume integral over the energy density. That would be the alternative, but yeah, we already have the formula for the capacitance, so that is more straightforward maybe at that point of time. So I have some more capacitor problems here. We could work on those. Or you have questions? Hmm? This one here? This is joule. This is, sorry, this is a J. It is a J. This is a J. Oh, that's also not so nice. This is a J. Or I don't know, you do the J more like, how do you do the J usually? Like this? This is a J for joule. I can show you this problem. This is actually the question number 10 from the tutorial book. So if you look at this capacitance, and you have seen how we um, could work with this equivalent circuit, so these elements when we have this geometry of the capacitor. So here it asks calculate the capacitance between the upper and the lower metal plate of the given configuration. You may neglect boundary effects, it means no stray fields, and you have a permittivity between the plates that is that of free space. So you basically have in part of the plate another third plate inserted in here. So if you depict that, you have here your top plate, you have here in part another plate, and then you have here your bottom plate. And we can divide that here in two zones, so to say. This here is a left-hand region where there is no third plate in between. This is your second region where you have the third plate in there. And we know that, as we saw in the lecture, we can introduce now here an equivalent circuit here, and that would contain here one capacitor and a second capacitor. And for the left-hand side, we would have a single capacitor here, right? So here, let's say this here is a separation D. This one is also separation D. Then these here would be separated by 2D. And here we have width of the plates, which is given by A, and also the depth here is also given by A. So we know what is the capacitor here. The general formula for a parallel plate capacitor is, but this of course is a bit more complex, but you see it is like an assembly of three parallel plate capacitors. The general formula is the epsilon times the area divided by the plate separation. So this is the general formula. And we see that this configuration corresponds to having here one parallel plate capacitor and here another one and another one. You agree with that? So we can denote these here as C1, C2, and C3. So this is our C1 here, C2, and C3. And we can, in the next step, so next step is that we can simplify this equivalent circuit that we have derived by making actually just a connection of two parallel condensators, a parallel connection of two condensators. The one remains our C1, the other one is our new C23, and this capacitor C23, that is C2 in serial or in series with C3. So you know what the formula is for connecting capacitors in series that we derived in the lecture. That is one, the series, the one that represents the two capacitors in series, the capacitor C sub 23. We obtain its inverse by adding up the inverse components of the individual capacitors in this series connection. So that would be C2 plus C3 divided by C2 times D3. And then we just take the inverse. C2, C3 is hence C2 times C3 divided by C2 plus C3. And that is what is our C2 now that we can obtain from the parallel plate capacitor formula. That is epsilon times the area and divided through the separation. The area you see is in the depths, it's here that is 1a, but here the width is only a half. And the separation of this here, it's just d, right? So we have a times a half divided by d. And that is basically epsilon a square over 2d. And this is also the same as our capacitor C3, right? Because they are identical here. You see C3 and C2 is a series connection of two identical setups. So take that and insert that here. So you get C2 is equal to C3. That means we have here basically C2 squared. And down there we have 2 times C2. And that makes it 1 half C2. So the capacitance on the right hand side, this C sub 2 3 becomes just 1 half epsilon times a squared over 2d. And now what is our C1? Well, now in the next step, we would like to connect these two and make these from these two parallel ones, we want to make a single capacitance in the equivalent circuit, and that we denote with C tot for C total. And this C total is a parallel connection, which I denote like that, of C1 and C2, 3. So what is C1? C1 is epsilon. Epsilon is a material parameter. And then A, what is A? This is again A in the depth and a half in the width. And D is now 2D. So that would give us A square over 2D. And because we are adding these two together, the other one we have up here computed is E a square over 2D. So we see actually that they are, sorry, I did a mistake here. This is this area is A times a half. So area is a square half and the separation is 2D. So I'm missing here a 2. And here we have 1 half times epsilon a square over 2d. That is also epsilon a square over 4d. So they are basically the same, and we add them up, and then we just obtain epsilon is a square over 2d. And now let's insert the actual quantities in here. We put in for the epsilon 8.5. What is given as permittivity? Oh, there's a the epsilon is given according to that is what it states, 8.85 amp per second per voltmeter, and you enter here 0.01 square meter for A is 10 centimeters, and here you get 0.02 meter, and then you get 44.3 picofarad. So in terms of units, you have here ampere second per voltmeter. That gives you, this is the epsilon times meter